Good morning. My name is Franziska Hinkelmann. I'm a software engineer on the V8 team, and I'll talk about performance profiling V8. So I think we can all agree that JavaScript is incredibly powerful, not only in what it can do, but also in how fast it can do it. If you think about it, that JavaScript, a scripting language, is powering Node enterprise applications or those big websites like Facebook and YouTube, that's pretty amazing. And of course, this performance of JavaScript is coming from the JavaScript engines. So in this talk, we'll look at what V8 is doing to be this fast and how to profile that. To put V8 a little bit into context, there are a lot of JavaScript engines out there. The big browsers, they have all their own engines. So there is Chakra Core, that's the engine in Microsoft Edge. And actually, right after this, Brian will tell us more about Chakra Core. Then there is JSC, JavaScript Core and Safari. There's SpiderMonkey and its monkey friends and Firefox. And then there is V8 in Chrome. And then Node.js, you can build Node.js running a Chakra Core as its engine, or your default Node.js installation comes with V8. So these four engines, they optimize for performance. They're pretty big, heavy engines. If you work on IoT and you are very constrained for memory and size, you might want to trade performance for memory and work with an engine like Ducktape or JavaScript. So here's a JavaScript CPU profile of a Node application. And if you do node -- inspect, then you can debug your Node app in the Chrome developer tools, just like you could do it for a front-end application. You can set breakpoints, step through the usual debugging stuff, and you can also create memory and CPU profiles. So here's a CPU profile, and you see in which function you spend how much of your time. And what you do see also is that, for example, here is related to, that function has a warning exclamation mark. And as you hover over it, it says, not optimized, optimized too many times. So V8, the JavaScript engine here, was trying to optimize something and not able to do that. So we'll spend the next 24 minutes looking into V8 details, what this optimization means and why it's failing here. In order to talk about profiling, a few profiling tools, and why this optimization is failing, we have to look at several V8 concepts. So we're looking at dynamic typing, just-in-time compilation, inline caches, the optimizing compiler, and de-optimizations. I hope you bear with me. It's going to be a little technical. JavaScript is dynamically typed. It's not statically typed like languages like C++ or Java or Rust. It's dynamically typed. The types of your variables can change all the time dynamically. So by types, I mean things like, is a variable an integer or a float or a string? But I also mean what class or what structure do the objects have. So here's a very basic object. What are its properties? What are the properties of this object? Well, there are x and y. Are those the only properties? No, this object also has all the properties of the objects in its prototype chain. So you can do object toString. ToString is a property of object because it's in a prototype chain. OK, so it's already a little complicated figuring out what the properties are. But can the compiler now rely on that if it sees object, that it always has the properties x and y's? Obviously not. At any time, dynamically, you can change the properties. You can delete a property. You can add more properties. Or you could change the prototype or something if you wanted. So the compiler really doesn't have any information about what the types are. Only at runtime, it can look at it and say, oh, OK, this object has an x and a y. And so because there is so little information, the compiler doesn't know at compile time what the types are. JavaScript is using just-in-time compilation. So we generate machine code during runtime, not ahead of time. If you look at a language like C++, it's clearly ahead of time. It's actually two steps. First, you compile your C++ program. The compiler has all the information from the types and generates optimized machine code. You get an executable, and as a completely separate step, you run this. In JavaScript, this is one thing. You say node server.js, and it's compiling your code and running your server at the same time. But so JavaScript can't do this because there isn't a lot of type information ahead of time. So we rely on just-in-time information, and we use feedback about the types while we run to generate better machine code. So one example I want to focus on is property access. Something very basic like object.x. You do this all the time. You have objects, and you use its properties. If you have something as simple as this, what all could happen for the compiler when you want to get this property? I mean, x could just be a regular property. OK, compiler gets this property. But also, object might not have a property x. One compiler has to figure out it's not there and then use undefined instead. Object might not have an own property x, but it might be on the prototype chain. So the compiler has to check further up in the prototype chain. Object might be a proxy. There might be traps for get, so a compiler has to invoke those. And then x might be defined as an accessor descriptor, so when you want to get the value, you have to actually call the getter function, which can have side effects both on object and all over your program. So object.x looks harmless, but for the compiler, it's a lot of things to do. And actually, if you look at the ECMAScript specification, so that's what specifies what JavaScript engines should do to give you correct JavaScript, the get, ordinary get of a property is defined in this long block. So it's not important that you read this in detail. I just want to give you an idea. This like very simple object.x has 8 different steps in the specification that have to be done. And so since you're doing property accesses all the time in JavaScript, you're always getting values and storing values into them, and this is so expensive, V8 has a few tricks to make this property accessing faster. So again, here's the load function. It's super basic. All it does is it gets a parameter and it returns object.x. And now we're calling this with a simple object that has the property x. So the first time we call this, the compiler has no background on what object is, so it really has to follow the steps in the specification. And eventually it figures out, OK, x is a regular value descriptor, just give me the value. And in this case, internally, the value for x is just at an offset to the pointer of object. So once the compiler has figured this out once, we now memorize this and put it in a cache. So we store away the information that if we have an object that has this shape, that is just the empty object with property x, which is an integer, then we say, OK, at this offset is where you can get the property. So we're not storing that if this exact object where x.5 comes in, that then the value is 5. No, we're storing for these shape of objects, always look at this offset. That's your value. And then we associate this cache with this property access right here. So this cache is specific for this one line of code. So now the next time that we call load, when we need to access object.x, now we can check the cache and say, hey, is the object that I just called you with, do you have something similar in your as a key? And if you look at these two objects, they look very much the same. They just have different values for x, but they have the same shape, so they have the same key in the map. And we can go straight to returning whatever value is at offset 1 internally. We don't have to go through these 8 steps, which if you do that a million times is very slow. So the name of these caches internally or externally, we call them inline cache, IC short. You have an inline cache always associated with the call side. So in this function, you actually have 2 inline caches, even though it's both times objects, both times x, and all in the same function. Those are completely separate inline caches. And we store in these inline caches, the keys are shapes of objects, and then the values are like shortcuts to get these properties. And I sort of abstractly keep saying shape of object. Since we don't have classes in JavaScript except as syntactic sugar, V8 is internally assigning to every object a hidden class or a map. So whenever I say map or hidden class, I mean this shape of an object, not the object itself. And 2 objects basically have the same map if they have the same prototype and exactly the same properties. So, and by assigning maps to every object and then using that for inline caches, we can immensely speed up property access. Since that's something you do all the time, this gives you quite some speed up. Inline caches, we distinguish between the states that they are in. And we care about how many keys they have. So what we like best if is an inline cache is monomorphic, mono, one, morphic shape, if it has just 1 key in it. And then we also talk about polymorphic caches. That's when they have between 2 and 4 keys in them. So very small caches. Whenever a inline cache sees more than 4 different maps, then it transitions to megamorphic. That's a little different than the mono and polymorphic caches because it's not a cache for this one call set anymore. It's actually one big cache for your whole application. So once an inline cache goes to megamorphic, you're slower because now you have to check all the cache entries for any object in the program. So it's best for performance if caches are mono or polymorphic. And if you want to figure out in what state your cache is in, you can actually do that because you can run Node with V8 flags. So -- trace IC is a V8 specific flag, but you can use all of them on Node. And if you have a script or server and you run that with Node, just do --trace IC. And you get tracing output that shows you in what state your caches are in. This is, in the terminal, it's a little bit hard to see anything useful. It's a lot of information. But you can use ICE, the inline cache explorer, create a tracing output, pipe it into a file, and then load it in ICE. And then here you see nicely in what state your caches are in. Here I actually... This is tracing of a real application and not just a toy file. So this has more than 1 million entries. You wouldn't want to look this in your terminal. In ICE, you get it nicely split up, and you can sort, for example, by state or by property key or by position in the file, and then see in what state most of your caches are in. So here I'm sorting by file position. And now if I look for the function that we saw earlier in the profile as a troublemaker with the exclamation mark, I can look at all the ICs for the property accesses within this function and then drill down on the details to figure out what's going wrong. So hidden classes and ICs give us speed up for property accesses, but that's not quite the performance yet that we need to do real-world JavaScript. So what actually every modern engine has is an optimizing compiler. So the modern JavaScript engines, they don't have 1 compiler, they have at least 2 compilers. And the way this works is that the basic compiler, the slower compiler, starts compiling and running your program first. And while it does that, it's collecting information and figuring out which functions are hot. So which functions are being run a lot. And then if a function is identified as hot, then the optimizing compiler takes over and compiles optimized machine code for that function. And if we combine optimization with the inline caches, that's where we get a huge speed up. And I'd like to show this to you on some actual machine code that comes out of it. So back to our basic example, a function that's just returning load.x of its parameter. If we run this a few times, always with similar looking objects, so always objects that have the same hidden class or map, then the inline cache associated with this property access is in monomorphic state. It has just one single entry. And now if this function is hot, is being run a lot, and the optimizing compiler takes over, then this is the optimized machine code that is being generated. So again, you can try this out yourself. Just do node -- print optimized code if you want to see this. And this might look like a lot, but it's really very little considering that it's machine code. So let's try to understand it. Up here is call stack check. That is where we enter the function. So this is the beginning of this function that's then going to return object.property. The next thing we do is check non-smi. Smi is small integer. We just internally have to make sure that object actually is an object that has a map and not just an integer internally. This should always be the case. And then we move on, and this is now where the inline cache comes in. So this check map here is comparing the map, the hidden classes of the object that we just passed into the function, to the map that was stored in the inline cache. So this address that you see next to the check maps, that's actually hard-coded into this optimized code based on what was in the inline cache. So we have inline cache, we optimize it, and we get this like fixed set of machine code, and it holds the actual address of the map that we want to compare against, because that's the only one in our cache. So we check the maps. If the object we passed in matches the map that is in the inline cache, then we can do the easy stuff. In this case, it's a load named field, which in our case was just return the value that is at the offset, at an offset to the object. So we're done here. If we call this function now with a very different object that doesn't have the same map, well, then the check fails, and it says jump to 91, which is down here, and that's actually a de-optimization bailout. So we have optimized code. We try to run it with a different object now. This might work, and we might be able to use what we've learned before and be done really fast. Or it might not work, and the optimizing compiler says, sorry, I can't handle this. We have to go back to the basic compiler and then do all these steps that the specification says very carefully to make sure everything's correct. So this is what the code looks like if your cache is monomorphic. This here is polymorphic code, polymorphic cache. So if there are 4 entries in your cache, instead of 1 map comparison, we have 4 map comparisons. And again, if the object you pass in, if it matches one of those maps, then we can just return the value at the offset. If that's not the case, then we have to jump down here and de-optimize. So we collect information for the inline cache. We can use this for faster property access. And then for hot functions, we actually generate better machine codes that's way faster than what you would get if you have to do all the slow lookups that you have according to the spec. And we can use information from the IC to quickly get to properties. So this is optimized code. If you're interested in seeing which functions are being optimized, when are they being optimized, and when does the de-optimization happen, that's also something you can see. So again, trace opt, trace deopt as a flag behind node. And then you see which functions are being optimized, a little bit of other information. And down here is where the load function was de-optimized. So if I call load now on a very different object, we saw in the optimized code, we have to bail out de-optimize. That's exactly this part here. And it actually says, evicting entry from optimizing code map. So what we do is this piece of code that we just saw, that's actually being thrown away, because the compiler said, well, that didn't work so well, let's throw this out and start over with the slow code. So back to the original problem of this function having a warning sign, not optimized because optimized too many times. Now we sort of understand what's going on here. we were calling this function several times. The inline cache got into a certain state. The function was being called a lot, so the optimizing compiler generated a piece of optimized machine code for this, and it was using information from the inline caches of that function. And then we were calling this function more, but now the objects seemed very different at some point, so we couldn't use this optimized code, I had to throw it away. We repeated this 10 times, and then the compiler said, it's better if we don't optimize it, because optimization is expensive. Generating this optimized machine code is more expensive if you do it just once than to run the slow code. So at some point, the compiler decided it's probably more performant to just give up on optimizing is related to and keep the slow version, because we keep de-optimizing over and over again. So by starting with profiling to identify some troublemakers, then looking at the inline caches, checking what exactly the keys are and the lines of code where the inline caches of that function, what their states are, looking at optimized code and looking into the source code, you can actually figure out which objects are causing the de-optimization at which parts, and you can make some ugly changes to the code to work around that. And so you can actually stop this function from being optimized and de-optimized all over again to get rid of this warning sign. So when you profile, again, is related to it doesn't get the exclamation mark anymore. But please be very, very careful with those kind of optimizations. Better not to make them at all. Obviously, you're creating very ugly code that's hard to read, because you're not it's not business logic anymore that you're implementing. If you put in extra if-else's and special cases, depending on what your object is, you're obstruing the business logic, and it's much more error-prone. But even if you can manage to do that correctly and can get people to still understand your code, you're optimizing for something that's internal to V8 and that's changing all the time. We are very actively working on the optimizing compilers. They are changing with every release. So if you make an optimization today, the next time you update Node, it might actually be much, much worse than if you had just left it to yourself. And then this should be obvious. These optimizations, other engines have other implementations. They work very differently. So if you optimize for V8, it will not work well with other engines, most likely. And you want to keep that flexibility that you can switch to other engines in Node. And in the front end, anyways, you have no say in what the user is using. So I hope I was able to give you a little bit of an overview how V8 works internally. And some of the tools if you want to play around with that yourself. Obviously, there is debugging with the Chrome developer tools, where you can create those profiles and look at them. And there's tons of different flags if you want more information about what's going on under the hood in the engine. There's trace optimization, trace de-optimization, just to see which functions are actually being optimized and are they being de-optimized again. Then you can look at the generated code, print opt code or print code to see the non-optimized code. And you can see the state of the inline caches, trace IC. And if you want a better user interface for the inline caches, use ICE, the IC Explorer. It's distributed together with Node and V8, so you find it in Deb's V8 tool if you want to use it. And if you have any questions, please find me at the conference. I'd be very happy to chat to you, or feel free to email or find me on Twitter. Thank you.